All right, everybody. So today we're going to start talking about radical chemistry in chapter 10. So this chapter is going to start off with a lot of definitions. And so I'm going to kind of go through this and define all these processes. So the definition of a radical reaction, well, a radical itself is a high energy electron deficient species that has a single electron, okay, in its atomic orbital that's highly reactive. So the way that these are often generated is through the process of homolysis, where you have a sigma bond between two atoms, basically splits into two radicals. So you get a decomposition. So one atom gets one electron and the other atom gets the other electron, and you end up forming two radicals. So the process of homolysis looks something kind of like this, where if we were to take, let's say, bromine Br2, and you were to expose that to some energy, which could be either in the form of light, which is abbreviated as H-nu, or with heat, well, then that will often cause the bond to essentially break, and each bromine ends up getting one electron, which is represented with this single dot here. Now, notice when we're talking about one electron transfer, you have these hook arrows, as opposed to two of like a double-sided arrow, which represents two electrons transferred. So pay attention to those subtle differences in the mechanisms. Now, one of the things that we can say about this is that energy in the form of light or heat may cause homolysis in weak covalent bonds. So some good examples of this are peroxides, which have a weak oxygen-oxygen single bond, or in halogens, which also have a relatively weak sigma bond as well. Radicals are highly reactive electron deficient chemical species and have pretty much the same kind of stability rules associated with them as carbocations, meaning they are trigonal planar, they are sp2 hybridized, and they prefer to be more substituted, meaning a tertiary radical is more stable than a secondary and is more stable than a primary radical. And when we talk about systems that are where you have double bonds that are on adjacent carbons, or even benzene rings, these radicals are in particular very stable because you have resonance with those adjacent systems where the radical is able to resonate with those pi bonds, and so that makes them even more stable. So we're going to talk about that in a little bit more detail in just a few minutes. Now, to get into some specifics, some actual numbers here, the energy needed to form radicals. So if we were talking about homolyzing a typical, sp3 carbon hydrogen bond, okay, like in methane, if we were to homolyze this bond so that each of these atoms got an electron, and we formed this methyl radical and a hydrogen radical. If we wanted to look at this species in a little bit more detail, talking about this particular radical right here, well, what I could say about that electron, so I'm going to try to draw this out three-dimensionally so you can see it. Okay, so what I'm trying to represent is that carbon is a trigonal planar, and that there is a p orbital here that lone electron exists in. And we would say that this position here, this carbon atom, is sp2 hybridized. Now, some things I can say in particular about this species. Number one, there is no resonance stabilization. Okay, so that's one of the reasons why this is a relatively high number, is because, well, that radical is pretty much centered on that carbon. there is pretty much no substitution on that carbon, okay? And we have an odd electron. On the carbon, which you're going to see with pretty much all of these radicals. Now, if we were to look at another system, okay, again, similar to methane, but a little bit different, a little bit larger system. So we were to look at ethane. Well, the energy it would take to homolize that particular carbon-hydrogen bond is still pretty high, but it's lower. It's lower than the 105 that we saw with just methane. Okay, so now why do you think that this is a little bit lower than the first one? Well, lower energy is needed simply because the radical is more substituted. So just like with carbocations, the more substituted a radical becomes, the more stable it is, and so the less energy it takes to homolize it. Now, if we were to build on that even further, we would see, the more substituted this carbon atom gets, the more stable the radical will become. But where you see even higher achievements of resonance stability are in allylic and benzylic systems. And so just a little bit of history here. An allylic system comes from the word allium, and allium is the word we use for garlic. And so garlic has a lot of these allylic compounds in it. And so here, if we were to look at this compound, 1-propene, you can see that we have a carbon atom here. So you put your sp2, sp3 hybridized carbon. It takes, about 10 kilocalories less to homolize, this carbon hydrogen bond than it did in ethane. So if we were to look at that, you would see the formation of this allylic radical. And you should notice that it is possible to draw a resonance structure with that species. And if I were to take that and look at a benzylic system, even less energy is required to form it. And so I can draw several resonance structures with that system and effectively march that electron into the benzene ring, just like what we would see with a carbocation as well. Now, those of you who are going into the second semester, you are going to see a lot more benzene chemistry in that class. And so I'm going ahead and drawing out all these resonance structures just to kind of show you how that radical is delocalized into the system, but to also get you used to drawing these benzene resonant structures, because you will see this kind of stuff a lot in 2342 in second semester organic. Okay, now as far as reactions are concerned, we're going to talk about a couple of these. The first one is going to involve the addition of radicals, so basically X2, into an alkane system. Now, alkanes are not very reactive, and in general, there's not a whole lot you can do with them. So if you want to try to install a functional group, this often is the only way you can actually get something on the molecule that you can then begin doing chemistry with. So what we can say about this process is that it is useful to be able to take an alkane and essentially replace one of its hydrogens with a halogen to make an alkyl halide, because, well, we've talked about alkyl halides all semester. You could potentially do substitution chemistry, elimination chemistry. There's a whole lot of things that you could do with these systems. The issue is you don't get a whole lot of flexibility with your halogen. A lot of halogens, like chlorine and fluorine, these are very reactive and will generally over-halogenate your system. You'll end up with halogens kind of going everywhere, especially with fluorine. And the problem here, again, showing you like what could happen with if we were to do a chlorination, is very likely you're going to see chloromethane, dichloromethane, chloroform, carbon tetrachloride, and HCl in a given batch with just one carbon. Now you can imagine how much of a problem this would be if there were even more carbons with more hydrogens. So that really kind of eliminates the utility of doing typical chlorinations. I'm not saying that there aren't methods to do it. I'm just saying that this is somewhat problematic. If we were to try to do this with iodine, it turns out that it's kind of the opposite. Iodine radicals tend to be too stable to react with alkanes, and so you don't really see very much of a reaction at all, very, very low yield. So it's one of those kind of Goldilocks and the Three Bears situation. The porridge too hot, the porridge too cold, the porridge just right. And so the just right halogen for doing this chemistry is bromine. Bromine radicals will add selectively into alkanes at the position where the carbon-hydrogen bond is on the most substituted carbon. Okay, so I know I'm skipping a lot of radical physical organic chemistry here in telling you this, but that is really the takeaway from this discussion is that bromine really ends up being our most practical species to do this chemistry with. So if you were going to take something like isobutane here and do a reaction with bromine in the presence of light, you'll notice that there is a carbon hydrogen here on this tertiary carbon. Then obviously there are hydrogens out here on the side. Now, as far as statistically speaking, if we were thinking about that everything would react equally, well, you would expect to see a whole lot of this compound here and very little of this one. But in reality, you actually see quite a bit of the substitution here on the tertiary carbon, which is exactly what we want in terms of practical terms, where it's going after the most substituted carbon-hydrogen bond to do the bromination. Now, the mechanism I want to go through with you guys so you can kind of see how this works. So the way that radical mechanisms work is in the following process. There are 3 stages that you should be familiar with. The first stage is what's called initiation. This is where you just form the radicals. Then in the second stage, you have propagation. Radicals react to form other radicals. And then in the third stage, you have termination. 2 radicals combine, producing a non-radical species. So if we were to do this reaction, let's say with that isobutane, and we were going to look at that system, well then your initiation step is going to be the formation of the bromine radicals. So you're going to start off with your bromine. It's going to undergo homolysis. and that's going to form 2 bromine radicals. Okay, so there's your initiation. Okay, now your propagation is going to be where your bromine radical is now going to start to react with your alkane. Now, it could potentially remove the other hydrogens, but as I've just spent the last 10 minutes saying, the one that's going to give you the most stable bromine radical, that's going to be your lowest energy of activation, is going to be the one where you get bromination or where you get hydrogen extraction on the most substituted carbon. So we end up forming HBr and this, this radical. Now, that radical can then go and react with another molecule of bromine. So by the way, this doesn't all convert. Okay, this is not a 100% process. This is you get just a few bromine radicals that start doing this, so you still have quite a bit of Br2 that's present in there in the system. Well, then now that can react with a bromine in Br2, and you get bromination and the formation of a new radical, which that radical now go right back up here and do this whole process again. And you're hoping that this is going to do this as many times as possible. But in this whole process, you're going to start to see some other things happen. Now, one thing that could obviously happen is 2 bromine radicals will recombine to form Br2. So in a large sense, there is reversibility here. But if this happens and we're still shining the bright light on it, so in other words, we have a constant light source, well, this can just go right back and form the bromine radical. So this is kind of the one that's the least problematic. The ones where you start to have issues is where, well, what if 2 radicals were to form that involve the organic molecules? Well, that would mean that you would end up forming species like this, which you will probably see a little bit of this in there, or you're going to start to see where the radical, the organic radical, reacts with the bromine radical directly, and you end up with the desired product, but of course no radical on this side. So once these start to dominate, particularly the bottom 2, well, then that effectively is going to end the reaction, and this is going to be probably the source of where you're going to start to see lower yields in your reaction, especially as you start to make this species. But this can be controlled, again, depending on your reaction conditions. But anyway, that's kind of the whole 3-step process of how these reactions work. Now, to get into something that is, directly affects what we have been talking about in this class, in prior chapters, in chapter 8, we talked about the process known as anti-Markovnikov addition. And I told you I was going to tell you about that later, how that worked. And so this is when I'm going to roll that out. So we see anti-Markovnikov additions when we are talking about radical additions into alkenes, particularly hydrogen halides. So if you have a hydrogen halide and it forms a radical, it generally adds in an anti-Markovnikov manner into it. And the reason why this happens is the halogen radicals add into pi bonds, as pi electrons are higher in energy, okay, than with sigma bonds. And so that ends up forming a new sigma bond on one side and a radical on the other side. So mechanistic, so the overall process is like this. Again, if you remember, if you were just to add HBr to this without the peroxide, you'd expect the hydrogen to add on the side of the double bond with the most number of hydrogen, the bromine to add here. But as soon as you add the peroxide or expose this to light, it reverses. You see the bromine adding here on the end and the hydrogen here on this position. So if we go through that process here real fast, what's happening is we have our initiation, and our initiator here is a peroxide. Peroxide homolyzes. And then once the peroxide forms, well, then we start to get peroxide radical or hydroxide radical, can then start to react with HBr, extract a hydrogen from it, the formation of water, and now bromine radical. Okay? Bromine radical can add into pi bond, and it's going to want to add on the end so that you get a more substituted radical. So in other words, the radical ends up being here at this position as opposed to being on the other position. So here this is a secondary as opposed to, say, if it added in the other way, which if it were to add here, the radical would be at this position, and that's primary. So we don't see as much of this as we do of the other one. So that's why you're seeing that bromine effectively going on the carbon on the end. Now, to finish this up, that secondary radical can react with another molecule of HBr, continue the propagation by deprotonating that, so you now have your anti-Markovnikov product, which is what we see up here, and the formation of a bromine radical, which can go right back up here and repeat that whole process. You don't need a lot of peroxide in order to get this to start reacting. Now your termination steps are, you know, the two bromine radicals could obviously combine to form Br2, you know, and another possibility here you could start to see is where the organic radical begins to add a second bromine, and you start to see some vicinal dibromide. There's really not a whole lot of this in here, usually just a trace amount, but it is detectable. And so your major product ends up being your anti-Markovnikov system. Okay, so I know I ran through that pretty quickly, but hopefully that terminology made sense. Again, if you didn't want to write all that down, the notes are available online, so you can kind of go through that. But make for sure you kind of make that connection between how radicals are similar to carbocations. The next section, the next PowerPoint, or excuse me, the next lecture I'm going to do is going to be, we're going to be finishing this chapter. We're going to talk about some other reagents and some other reactions that I want you to be familiar with as far as radical reactions are concerned. And then we will be moving into chapter 11, which is the last chapter in this course, definitely this week. So we'll be moving into it this week. So anyway, I hope everybody's doing okay, and I will speak to you guys again soon. Take care, and bye-bye.